When it comes to fighting cancer, the first step is pretty obvious. You gotta know your enemy. But what if we've been chasing the wrong guys this whole time? Let's get into it, because some new research is completely flipping the script on how we find cancer's real masterminds.
So, for decades, the logic was super simple. You look at thousands of cancer patients, you count up all the gene mutations, and whichever gene pops up the most, well, that's your number one bad guy. It just makes sense, right? The most common criminal has to be the most important one.
And this approach gave us a pretty famous lineup of villains. I mean, you've probably heard of some of them. Genes like TP53, PI3CA, and KRAS, these guys are mutated in a ton of different cancers. They're the usual suspects that pop up at every crime scene, and believe me, we've spent a huge amount of time and money trying to figure them out.
But this is where things get interesting. Researchers started asking this really crucial question. What if the guy we see everywhere isn't the kingpin? What if he's just a common foot soldier? And the real mastermind is somebody we barely ever see, but who's way, way more dangerous.
Okay, so let's first break down the old school way of hunting for these cancer genes.
And look, the frequency model makes a lot of sense. I mean, if you see the same mutated gene again and again in different tumors, it's a pretty safe bet that it's a driver, a gene that's actually pushing the cancer forward. This thinking has been the foundation of cancer genetics for a really long time, and it's been super useful. But there's a potential flaw in the system. Let's go back to that criminal analogy to see what I mean.
Okay, picture this. You've got two kinds of crooks. First, there's the foot soldier. This guy's everywhere. He's a common mutation, but honestly, he's kind of weak. For him to really cause trouble, to actually start a cancer, he needs a whole gang of other mutations backing him up. Then, you've got the mastermind. You don't see this one very often, but when you do, wow. This mutation is so powerful, it can start a tumor all on its own, maybe with just a tiny bit of help. See the problem? The old way of just counting heads is great for spotting the foot soldiers, but it could be totally blind to the real masterminds.
So this leads to this really cool new idea. If a mutation is a true powerhouse, a real mastermind, why would it need a big messy crew? It wouldn't. It doesn't need the help. So the thinking goes, the strongest cancer genes must be hiding in tumors that are otherwise really clean, the ones with the fewest total mutations. They're lurking in the quietest neighborhoods, so to speak.
Okay, so how do you test a hypothesis like that? Well, you need a new tool. You can't just count mutations anymore. You have to find a way to measure a gene's raw, unfiltered power.
And this is it. It's called the Normalized Driver Strength Index, or NDSI for short. This thing totally flips the old model upside down. Instead of giving points for being common, it gives the highest strength scores to genes that are found in those really quiet tumors, the ones with very few mutations. Basically, it ranks genes by how well they can work alone. And the way it works is actually pretty brilliant. It's just two steps. First, you take a ton of patient data and you sort their tumors. On one side, you put the quiet tumors that have just a couple of driver mutations. On the other, you put the really noisy ones with tons of mutations. Then, step two, if a gene shows up in one of those quiet tumors, it gets a really high strength score. If it only ever shows up in the noisy, crowded ones, it gets a low score. It's so simple, right? But it changes everything.
All right, so they've got this new tool. What happens when they use it? Let's get to the results, because this is where we see a whole new most wanted list for cancer.
So the researchers ran the numbers on this massive database of tumors, and the results were just, wow. The list didn't just get shuffled around, it was totally rewritten. A lot of the famous old bad guys got kicked right off the list, and a bunch of new names took their place. I mean, just look at this comparison. On the left, that's the old list, ranked by how common they are. You see the usual suspects, TP53, PIK3CA, but look at the list on the right. This is the new one ranked by strength. The number one spot is a gene I bet you've never heard of, GTF2I, and you see all these other new names popping into the top 5. Now, BRAF is interesting. It's high on both lists, which means it's both common and super strong. But here's the kicker. TP53, the gene that's mutated more than any other in all of cancer, it doesn't even crack the top 50 on the new strength list. That's insane.
So, who are these new masterminds? Well, think of them less as general thugs and more like highly specialized assassins. GTF2I, our new number one, is a crazy powerful driver, but it really only shows up in a rare cancer of the thymus gland. Then you have GNAQ and GNA11. They're the undisputed bosses in a type of eye cancer. And IDH1 and IDH2 are huge players in certain brain tumors. See the pattern? These guys aren't trying to do everything. They are absolute specialists, and in their own territory, they are devastating.
One of the researchers put it perfectly. They said a mutation in one of these genes can often single-handedly drive cancer in its specific tissue type. Single-handedly. That's it right there. That's what makes a gene a true mastermind.
Okay, this is all super interesting science, but so what? What does this actually mean for treating patients? Well, let's talk about the real-world impact of going after these masterminds.
This is where it gets really promising. Remember GNA, one of our new top 5 masterminds? Well, it turns out it belongs to a big family of proteins, a family that we already have a ton of drugs for. Get this, something like 36% of all FDA-approved drugs target this protein family for one disease or another. That's a huge deal. It means we might already have a playbook for how to shut these guys down.
So at the end of the day, this new ranking system isn't just about shuffling names on a list. It's a roadmap. It tells scientists and drug companies, hey, focus your energy here. These are the guys that pack the biggest punch. It lets us stop wasting time on the foot soldiers and go straight for the kingpins.
And that kind of leaves us with a bigger question, doesn't it? This whole idea, looking for strength instead of just frequency, looking for the rare powerhouse instead of the common grunt, that doesn't just have to apply to cancer. What happens if we start using this lens to look at other complex diseases? What other hidden masterminds could we finally uncover?